Okay, greetings everybody to the special lecture series in the PDE seminar. It is my pleasure to introduce Robert McCann from the University of Toronto. Just a brief bio. Online there is a bit more prepared by on the website for the lecture series. So Robert got his PhD at Princeton under Elliot Lieb, and after that he had a postdoc at Brown, which is actually where I happened to meet him the first time, and since then he has been at the University of Toronto. A few years ago, among his many travels, he traveled to Seoul as an invited lecturer at the ICM, and so his interests are in optimal transport, calculus of variations in that connection, mathematical physics, and he's also quite interested in applications to economics. And I'm not quite sure, that sometimes that also has differential geometric and general relativity connections. So he's a bit all over the place. And he is an engaging speaker, so I'm very fond of him being around today. So by generosity of the authorities, we're allowed to cross the US-Canadian border by Zoom, regardless of whether there is a pandemic or not anymore. And so due to that benefit, we have him around for today and for 3 more lectures in the following weeks. Okay, the podium is all yours.
Okay, well, thank you very much, Jochen, for the nice introduction, and Tuuk for arranging and inviting me to give these lectures. I'm very happy to be here. I'm sorry I can't actually be in Knoxville today. And I'm going to talk about joint work with Cameron Davies, who's now a PhD student in my department, and Tong-Suk Lim, who's a tenure track professor at the Krannert School of Management in Purdue. And I'm going to talk about pattern formation in particle systems from spherical shells to regular simplices. And there's a version of the slides online, except just click on talk at my website to get a version of these slides. And maybe this, as Jochen mentioned, the subsequent lectures are going to be on different subjects. And so I hope to post them at talk 1, talk 2, and talk 3, but this will be talk blank. And so the kind of models that we're going, so Tong-Suk and I started working on these models 3 or 4 years ago, and Cameron joined the collaboration about 2 years ago. And the kind of models that we're talking about are often used to model the kind of patterns that you see when animals are milling or flocking. So this is a flock of birds or swarming, and here's a school of fish. And the bottom view. The presumption that mathematical biologists start with is that the individual organisms in these models are, they're adjusting their behavior based on what their neighbors are doing. And that there should be some kind of simple rules that the individual fish are following that lead to these kind of complicated patterns that emerge, like the mills and swarms that we've just been looking at. And models like this go back nearly 100 years. Of course, you've probably seen them in the physics literature, where there's the Leonard-Jones model for molecular interactions, which presumes that things are repelling with, I guess, power -12 and attracting with power -6. And another chemist, Parr, a few years later. And they've been used in the mathematical biology world since the 1950s. So Breeder proposed an attractive repulsive power law interaction for fish separation. And about 50 years ago, Keller and Siegel wrote down their famous model for cell chemotaxis, where cells, maybe they lay down secretions and other cells move towards the secretions, and so the cells tend to clump together. And more recently, mathematical analysts in the last 20 or 25 years have been paying an increasing amount of attention to these problems. And so I guess I wrote down there are different kind of dynamics associated with these patterns, first order and second order dynamics. And I wrote down some of the names of people, and there's really a large community now doing analysis and simulations, and I've written down an incomplete list. And this is a little, I'm afraid this is a sort of a Canadian chauvinist talk. So I was giving a version of this talk earlier for a Canadian audience, and I colored the Canadian names in red, but you can disregard that. So here's the model. This is going to be a model on Euclidean space, although it turns out that these kind of models are also connected to problems in geometry that go back to the Hungarian school, like people like Fejes Toth and Erdos. So Tongsuk Lim and I also have a preprint on, so the work I'm going to describe today is based on two preprints that are joint with Cameron Davis and Tongsuk Lim. But if you look, all my preprints are on my website, also the archive. Tongsuk and I also have a preprint about a kind of similar model where the particles are constrained to live on the sphere, or actually the projective sphere, which there's a conjecture of Fejes Toth that goes back to the 1950s that's still unresolved in that context, and we made a little bit of progress. Okay, so today the particles, the organisms, whatever they are going to interact through an attractive potential given by a power A of this distance between them, and a repulsive potential given by a smaller power B of the distance between them. And I've normalized these potentials so that the difference is minimized at unit separation. So when the powers are negative, the profile of the potential would look like this. It would decay at large distances and blow up at small distances, and the minimum's at 1. That's probably the region of most physical interest. Although actually today I'm going to talk about the opposite region up here in the AB parameter space, which is sometimes called the mildly repulsive regime, where the exponents are positive. And in fact, V is going to be either 2 or larger. So there's the singularity at the origin is going to be smooth, at least C2 smooth. This minimum separation is still going to occur at unit distance, and the potential is going to be very strongly confining at large distances. Now, somewhere in between the physical regime and the mildly repulsive regime, there's a rectangle here that was identified by Lopez 4 years ago, where the quadratic energy, the two-particle energy associated with this potential becomes convex. So of course, in this green region here, the minimizers because of the convexity, the there's at least always a spherically symmetric minimizer. But outside of that region, lots of different things can happen, and that's one of the things that I want to explore a little bit today. So if one wants to think, I'm mostly going to be talking about energetics and static models. As Jochen said, I'm sort of a calculus of variations guy, but if one wants to think about dynamical models, you can describe the dynamics using either an ordinary differential equation or a partial differential equations description. So in the ODE description, you would keep track of particle locations for J particles. And what I've written down here is the first order model, where every particle sees its J-1 neighbors and experiences a central force, which is repulsive at short distances and attractive at large distances. If you want to write down a PDE model, then you write down the measure that represents the density of the particles that are doing the interacting, and that measure is going to satisfy a conservation law. So the so-called aggregation or self-assembly equation, and it takes the form of a continuity equation where the rate of change of the measure is given by a divergence of a flux, and the flux is quadratic in the measure. So the velocity driving the motion is the gradient of the interaction of the particles with all of its neighbors. So V, the potential V convolved with the distribution mu. And notice that V convolved with mu is actually the variational derivative of an energy, where the energy is the pair potential, associated with this interaction. And it's always a quadratic energy. And so minima for this energy are going to be fixed points. Both local and global minima are going to be fixed points for this dynamics. And you kind of expect the minima should be attractive because this energy is dissipating. This is a Lyapunov functional. It's always going down in time under this dynamic, under the aggregation dynamics. And so I'm mostly going to be thinking about the continuum limit where the number of particles has gone to infinity. And the dynamics then defines a flow on the set of probability measures on Rn or on a subset K of Rn. And it's often going to be convenient, since I'm dealing with strongly confining potentials, it really doesn't cost me any generality to restrict my attention to compactly supported measures. And because the energy that we just saw is translation, and here it is, it's translation invariant because only x minus y matters. And so it's convenient to normalize the distributions I'm going to deal with to have center of mass at the origin, and I'm going to indicate that by a superscript 0. And I should mention, I think my collaborator, Cameron Davis, is following the talk. So if you post questions in the chat, maybe he can answer them for you. Okay, so but if one wants to talk, so you expect minimizers to represent attracting fixed points to the flow, and that should be true for both global and local minimizers, but actually the topology that if you want to talk about local minimizers, the topology is very subtle. And somehow I knew this problem already from my thesis 25 years ago when I was thinking about a very different kind of sounding problem, which is the problem of rotating stars. So you imagine a star is a collection of particles or a mass of gas, and maybe the total amount of gas is fixed and the center of mass of the gas is fixed at the origin. And you'd like to try to minimize the total energy of the gas, which consists of gravitational interaction that's trying to pull particles together and make the gas collapse to a point, and some kind of internal energy. The particles are maybe fermions, so they don't all like to be in the same place. And so there's some or they obey some equation of state that provides a pressure. And so when you squeeze them, they push back. And if you ask, can these two forces equilibrate with each other under some reasonable assumptions, the answer is often yes. And if the gas is not moving, there's a global energy minimum. But then if the gas is moving a little bit, then another conserved quantity would be its total angular momentum about its center of mass. And if you try to minimize the energy subject to a constraint on a non-zero angular momentum, you get into a bit of difficulty, because it turns out that somehow there's some kinetic energy associated with the rotation, and you can always reduce the kinetic energy by taking a teaspoonful of mass and putting it in orbit very far away, where it has a lot of angular momentum and very little kinetic energy, and then stopping the rest of the rotation. So you can create a satellite, and in that way you can satisfy the angular momentum constraint with very little kinetic energy. And on the other hand, somehow this sounds like a very discontinuous operation, taking a teaspoonful of mass and teleporting it far, far away. And so you need to choose a topology that makes that operation discontinuous. And all of the vector space topologies fail to do so, because this kind of interpolation is continuous. Evaporating mass, say on the lighter component of a binary system, if you evaporate the atmosphere of the moon and bring it to the Earth, you can maybe lower the kinetic energy, but somehow it looks continuous in a mathematical sense, but in a physical sense, you have no way to get, there's a potential energy barrier that you have no way to get the mass across. Okay, but so coming back to these interacting particle systems, I'm showing you some simulations here. This is actually not power law potentials. This is piecewise quadratic potentials. And the piecewise quadratic pieces depend on two parameters, A and D. And the point of this slide is just to show you that depending on the parameters you choose for your interactions, you can get a lot of different patterns emerging from, rather discrete things happening down here to very continuous smeared out things and spherical shells or rings. And if now this is actually for power laws, where I think the attractive power is fixed to be 5, and in these are three time series, 1, 2, and 3, that correspond to different choices of the repelling power, 1/2, 1 1/4, and 3 1/2. So one of them is in the mildly repulsive regime. And so in the mildly repulsive regime, you start out with a ring of particles and you wait for a while, and all the particles clump to 3 points, which are orbiting each other under whatever dynamics is being studied here. If you move out of the mildly repulsive regime, then depending on how far you go, either the particles concentrate on a circle or they smear out into something that's absolutely continuous with respect to area. So these are the kind of patterns that we set out to try to understand. This is a simulation by Albee and collaborators from 2014. Now, so the simulation results I just showed you maybe come from this point and this point and this point. All the results I'm going to talk about today come from the mildly repulsive triangle up here. And again, nearly 10 years ago, Balaguer and collaborators showed that even local minimizers, never mind global minimizers, of this energy among probability measures. If B is less than 2, then they have the Hausdorff dimension of the support is positive. And the more negative B is, the larger the Hausdorff dimension of the support has to be. This is within limits. So I think, B probably has to be bigger than dimension than 2 minus dimension, so that this never becomes larger than the dimension. And but for in the mildly repulsive regime where B is bigger than 2, this result tells you nothing. On the other hand, there is a result of Carrillo, Figali, and Patachini, more recent, which says when B is bigger than 2, then again, local minimizers, and in particular global minimizers, are supported only at isolated points. And in between, relevant to us is this work of Sun, Uminsky, and Bertozzi from 10 years back, who showed that on this line separating the mildly repulsive triangle from the non-mildly repulsive triangle, the spherical shell solution is actually linearly stable if A is not too large, and it becomes unstable if A is bigger than 4, and the vertices of a regular simplex become linearly stable if A is bigger than 4. And so there seems to be some kind of exchange of stability, and they left open the questions of nonlinear stability and whether there's a global attraction in these problems, and those are two of the questions I want to address today. And Sun, Uminsky, and Bertozzi, they were actually motivated, they were studying the purely attractive Keller-Siegel model. So they're studying a model where all the particles are going to find their way to the origin, and at some rate that they're able to calculate. So it's purely attractive with an attractive power A, and they knew the rate at which things were coalescing towards the origin. And they said, well, let's view this picture from a receding distance so that the coalescing particles don't coalesce anymore, but rather they stabilize to some characteristic shape. And then we can ask what that shape is. And the effect of viewing it from a receding distance is equivalent to putting in a repulsion with power B equals 2. So somehow that's how they got from their purely attractive model to an attractive repulsive model. And finally, in one dimension, there's work of my collaborator and his collaborators where they more or less give a catalog of local and global minimizers. It's not a complete catalog, so people are still working on this. And in fact, our work inspired some progress by Rupert Frank in one dimension. But the results I'm going to talk about today are all higher dimensional results. So I've drawn the picture for dimensions 2 and higher. The picture would be a little different in one dimension. And basically what I'm going to talk about a couple of different regimes. So I call this line B equals 2 the centrifugal line, because as I was mentioning in the model of Sun, Uminsky, and Bertozzi, B equals 2 corresponds to a repulsion, which is like the whole system is on a turntable rotating at constant velocity, and that's tending to throw all the particles outward. And then whatever power A you have is tending to hold them in, and you want to understand what pattern forms. So if A is less than 4, along this segment here, we're able to show that the minimum is unique and spherically symmetric, and in fact concentrated on a spherical shell of thickness 0. So I mean some radius, but non-zero and 0 thickness. So here spherical shells minimize. And on the other hand, if I'm in this region above the 0.42, the uniform distribution over the vertices of a unit simplex, so all these points are distance 1 apart, an equilateral triangle in 2 dimensions or a tetrahedron in 3 dimensions of side length 1, is the unique minimi. So balanced unit simplices and their translations and rotations uniquely minimize. At this point here, of course, both the spherical shells and the balanced unit simplices minimize, but actually there are a lot of other minimizers as well at this point. And we were also able to show that there's some line along here, A equals AN of B, so, and we know it's monotone and continuous and strictly decreasing, such that to the right of that line, the simplices uniquely minimize, and to the left of that line, simplices do not minimize. And we're able to give a partial description of what's happening along the line itself and say something about where the line falls. So somehow that is the agenda for today. Are there questions?
Just a quick question. Is this picture for any dimensions?
Yeah, so for any dimension bigger than 2. In one dimension, things are a bit different. So in one dimension, the critical point would occur at 2, 3 instead. So I guess in one dimension, a spherical shell and a unit simplex are the same thing. So, you know, it's in each case, it's a Dirac mass at distance 1/2 from the origin. Equal Dirac masses 1/2 on either side. That's the the 0-dimensional spherical shell, and it's also the 1-dimensional unit simplex.
And can you remind us the potential again? We have the power A minus B or what?
That's right. So VAB is x to the A over A minus x to the B over B.
Okay.
Great.
Thank you.
Thanks for the questions.
And good question. Are these also equilibrium solutions if you do the dynamic problem when time goes to infinity? Will they converge to any of these, or just these are stationary ones?
So they're the global energy minima. So you would expect them to be attracting. It turns out that that's actually a subtle question. I'm going to have more to say about that later. But it turns out that they're stable in the sense of Lyapunov, but they're not asymptotically stable.
Okay.
All right. At least, so the simplices are probably asymptotically stable, but the spherical shells are not asymptotically stable. Okay, and so here I have a slide where I basically repeat what I tried to draw in pictures, but I repeat it in words here. So if A is if B is equal to 2, so on the centrifugal line, and A is between 2 and 4, then the energy is uniquely minimized among centered distributions by a uniform distribution over a sphere of appropriate radius. Now, if A is equal to 4 and B equals 2, then every measure on the sphere of this radius that happens to have moments of inertia tensor proportional to the identity matrix is a minimizer. So that includes, you know, you can have ring solutions in 2 dimensions. You can have the Platonic solids in 3 dimensions where you'd put the same mass at each of the corners of the vertex. You can have a lot of other things. You can have convex combinations of these. So that's one thing that's really peculiar about this point here is the set of, over here, the set of minimizers is finite dimensional. I mean, it's basically just the spherical shell and its translates. So n dimensional. Over here, it's finite dimensional because it's just the balanced unit simplex and it rotates and translates. So it's a little bit higher dimensional than here, but not much. Here, you suddenly have an infinite dimensional space of minimizers. And finally, there is this continuous strictly decreasing function A2, AN, which depends on dimension, passing through the point 4, 2, such that on one side of that line, the simplices are the unique minimizers, if the inequality is strict. And on the other side of this line, this is if and only if, so on the other side of this curve, the simplices don't minimize, the unit simplices don't minimize. And I should say that, so this is somehow the 2 preprints that we have out are progress relative to 3 or 4 years ago when Tong-Suk and I worked on this problem. We were able to show a result like this, but only for A very large. So only far to the right in this were we able to describe the global minimizers. However, we were able to say that for smaller values of A throughout this whole region, the simplices were still local minimizers, and that fact is going to have a role to play in the analysis today. And we're actually able to estimate where this transition threshold falls in this following indirect way that I don't sort of expect you to learn the formulas, but it's very concrete. So there's, for each dimension, there's some curve, Fn of A. So this is A and this is Fn of A. And you pick a value of B, it turns out this is a unimodal function of A. So it goes up and then it comes down. And whatever B value you pick, there's exactly one other A value where Fn of A equals Fn of B. And that value gives a lower bound for the location of this line. And if you let the dimension tend to infinity, then you get this function here, which is still unimodal. And if you take the a value matching a given b value for the infinity value of this function, you get an upper bound for the location of this line. And so we're able to say where this line falls, we're able to give this, so then my notation's a little bit different in the paper than in the talk, but we used alphas and betas instead of a's and b's. But so this is the upper bound. This red line is the upper bound. The blue line is the lower bound, and the purple line, the real thing, is somewhere in between them. And somehow the upper bound and the lower bound converge as the dimension goes to infinity. So we know exactly where this purple line lies when dimension approaches infinity. And again, everything above and to the right of the purple line is uniquely minimized by simplex, and everything below and to the left of the purple line, the simplex is not a minimizer. And so we really don't, we know on the boundary here it's a spherical shell, but we don't really know what's going on in here at all. This is unknown.
That brings up a question, actually.
Yep.
So when you say you don't know what's going on, does that mean you've ruled out the possibility that you still have local minimizers in that red region?
The simplices are still local minimizers in the red region, but we know they're not global minimizers anymore.
Okay, so there could be another global minimizer elsewhere, possibly.
There has to be another global minimizer elsewhere.
And I believe also like Carrillo, Figali, and Pattacini's like work suggests that inside the red region, like the global minimizer has to have like only finitely many points in its support.
Right, so it can't be a spherical shell because a spherical shell has infinitely many points in its support. And we know it's not a simplex, so it has to be something else, but we don't know what it is.
Okay, all right, thanks.
Yep. And so along this transition line, we are also able to give a characterization of what happens, how the stability or the global stability of the simplex fails. So we say at least one of the, so my notation is that this is the set of probability measures which are rotations and translations of one of these balanced measures on a unit simplex. And so this is exactly the set of minimizers to the right of this critical line, but along the critical line, either there are other minimizers outside this set, or else when I look at the potential, so I'm sort of skipping ahead here, but the Euler-Lagrange equation for this problem would be that the variational derivative of E with respect to mu, which is VAB star mu, if I was minimizing subject just to an integral constraint on the total amount of mu, then this would be equal to some Lagrange multiplier. But I'm also minimizing to the constraint that mu is non-negative. And so it turns out that I can't, where mu is 0, I can only perturb, I can only add mass, I can't take it away. And so that means the Euler-Lagrange equation becomes that this is bigger than or equal to constant on Rn with equality on the support of mu. So in other words, if I look at the set of minimizers of VAB star mu on Rn, the mu has to assign full mass to that set. That's the Euler-Lagrange equation. And but of course, this set can be bigger than the support of mu in principle. And one of the things that can, if all of the minimizers are still rotates and translates of a unit simplex on this critical line, then it has to be true that this containment of support of mu in this set of minimizers is strict. And so somehow, if you think about bifurcation theory, if you think about, so here's a caricature. If you think about the problem of minimizing x squared minus 1 squared, which is some, it's a W-shaped potential that's minimized at plus and minus 1. Like so. I hope it's like so. And then if you perturb that with some amount of, I don't know, x squared, and you take epsilon to be large enough, then at some point, this picture is going to transition to a picture like this. And so where these two different minimizers come together into a single minimizer, but it happens continuously. They move closer and closer as epsilon gets larger and larger until you get to this picture. And on the other hand, if you perturb this W potential with like epsilon x, then what happens is that when epsilon is positive, the minimum's over here, and when epsilon's negative, the minimum's over there. And at epsilon equals 0, you get a discontinuous transformation where the minimum jumps from here to here through this kind of picture. So I'd call that a discontinuous bifurcation. And what these two things are telling us is that the picture along this critical line is somehow analogous to the second picture here and not to the first picture, because we don't have a single, if I run this story backwards, we don't have a single minimizer splitting continuously into two nearby minimizers that can get further apart. Rather, there has to already be at finite distance a minimizer outside this set that wasn't there if I was just above this line, or else this potential, whose minima are concentrated at the support of the optimizer, suddenly touches down somewhere else. And so instead of mass just being here and here, you might want to put a little bit of mass somewhere far away. So that's what this characterization is telling us. Okay, and so I guess that those are most of the results that I want to talk about today, and I'm going to spend most of the rest of my time sketching some of the ideas of the proofs, unless there are questions. Okay, so let me go back. I guess I should remind you what the results were once more. So I'm gonna spend some time talking about these first two results. What happens along the frontier if A is not too big? Why do I get a spherical shell minimizer? And then at the end of that segment, at the end of this segment here, why do I get all these other minimizers? And then later I will talk about what's going on up here and describing this line a little bit. So in the region where A is between 2 and 4, Lopez showed a few years ago that there's a hidden strict convexity in the problem. So I'm dealing with a quadratic energy. And so convexity should mean that the quadratic energy is positive definite. The Hessian of the energy is proportional to the energy because it's quadratic. And of course, my energy is not positive definite, but I'm only interested because I'm willing to look at mass measures mu that have center of mass at the origin. And whenever I look at two measures, mu naught and mu1, they're both probability measures, so they both have the same mass. When I look at perturbations, or like the convex curve that takes you from mu naught to mu1, the direction of this curve is a measure rho, which is neutral. It has 0 mass. And it turns out that when you restrict this energy to neutral measures with center of mass at the origin, then it becomes positive definite. So in this range, Lopez, this is a convolution of rho with the potential integrated against rho, and he shows using Fourier analysis that becomes positive. So this becomes positive definite. The constant, in other words, is positive, at least in this range here. So at least for A strictly between 2 and 4, the minimizer has to be unique and spherically symmetric. Well, okay, so I'm not just trying to minimize EA, I'm trying to minimize EA minus EB. But it turns out that at the end point of this range, when B equals 2, although the energy d mu, sorry, this is x minus y, d mu x, d mu y. Again, the energy is, well, it even looks positive definite. Yeah, it looks positive definite, but it's not. If I replace mu by something neutral, it turns out that this thing is an affine function of t along lines like this. And so the strict convexity of the attractive part of the energy balanced with the neutral convexity of the B part of the energy boils down to telling me the minimizer is unique and spherically symmetric. And now we said more than that. We said it was actually concentrated on a spherical shell of some radius and 0 thickness. And that follows from the Euler-Lagrange equation, which I sort of explained I tried to explain where this equation comes from. And one further observation, which it sounds kind of trivial, but it's actually highly non-trivial. So if mu is spherically symmetric, so I don't know how to write this, but if d mu of x is somehow d mu of absolute x, then when I look at this potential and I look on some ray through the origin, it turns out that has positive third derivative. So A is bigger than 2 here. And you can kind of, so of course, when the measures, if I took mu to be a Dirac mass, then I would be looking at RA over A minus r squared over 2. And if I differentiate this 3 times, I get, a times a minus 1 times a minus 2 times r to the a minus 3, over a. The derivative of this, the third derivative of that vanishes. And of course, okay, this thing is positive for all r positive. But what's very non-trivial is if I move from a Dirac mass to a spherical shell at some distance, if you can do it for one distance, you can do it for all distances, and I average this potential over a spherical shell, then you still get something with positive third derivative. And this is a little bit like, it somehow reminds me of Newton's theorem. If the powers were negative instead of positive, Newton's theorem says when you look at this for a spherical shell, you get a potential that's constant on the inside and decays like 1 over x in 3 dimensions on the outside. And so something very singular happens at the boundary of the spherical shell. But for us, it doesn't happen. It's the potential is actually C3, except possibly at the origin, and its third derivative is positive. And so what does it mean that it has positive third derivative? It means either this potential is globally strictly convex, or else it starts out concave, and then at some radius, its second derivative vanishes and it changes convexity, but it can only go from concave to convex because the third derivative is positive. It can never go back to concave. And so the overall profile of the potential, V of E1R, is either this picture, globally convex, or concave near the origin, convex further away. And the point is that when you have concave near the origin, convex further away, you have a unique minimum. And since the Euler-Lagrange equation said that the support of mu had to concentrate at the minimum of V star mu, all of the mass of mu has to lie at this radius, whatever it is, call it R star. And so that's how we get a spherical shell. So now if I move to the critical point where A is 4 and B is 2, things are still convex, but they're not strictly convex anymore. And so I can have so there's at least one sphere, because they're convex, if I take anything with center of mass at the origin and I average it with all of its rotations, the energy of the average can't be any bigger than the energy of the thing I started out with. And so by averaging with all of its rotation, I'll get something spherically symmetric. So there will be a spherically symmetric minimizer, but not all of the minimizers are spherically symmetric. And somehow, again, if you think about, if you think about the energy E2, which was 1/2 x minus y squared, d mu x, d mu y, it looks quadratic. But when B is 2, it's not really quadratic. So if I expand the square, then I get something like integral x squared d mu x, and the y integral goes away. And then maybe I get a term like integral with the center of mass squared, but I've been normalizing the center of mass to be 0. And so because I've normalized the center of mass to be 0, what I get is actually linear in mu and not quadratic at all. So that this thing becomes affine linear on the set of centered probability measures. And if I do a similar computation with E4, I find out that I expand oops, that's not what I wanted. I expand 1/4 x minus y to the 4th. And if I get a term like 1/4 x to the 4th, but if I integrate that against a neutral measure y, then it's the integral in the y is going to be 0. So that doesn't survive. And similarly, terms like x squared x dot y don't survive because the center of mass of the y variables is 0, is normalized to be 0. And so the only terms that survive are terms like x squared y squared or x dot y squared. And so these terms lead things to be strictly convex unless the two measures in question that have center of mass in the origin have the same second moment tensor. So I wrote the second moment tensor here. And it turns out when they have the same second moment tensor, then again, things become linear. And so you become affine linear. And this is a clue that allows you to kind of characterize what the minimizers look like in this situation. So in particular, the difference between this linear guy and this guy that's mostly strictly convex, but linear along guys that have same second moment tensor. So one of the minimizers is going to be spherically symmetric. And all of the other minimizers have to share its moment of inertia tensor, which will be proportional to the n by n by identity matrix. And so among measures mu that are have center mass at the origin and moment of inertia tensor proportional to the n by n identity matrix, Jensen's inequality tells you can relate the fourth moment of mu to the second moment squared. These were the other surviving terms, and this is E2 over here, maybe 2E2. And strict inequality will hold here unless x squared is exactly the trace of this, n times c. And so that's the thing that tells you that all of the minimizers of this guy have to live on the same sphere, but they don't have to be uniform on that sphere. They can be concentrated on different subsets of the sphere, so long as the moment of inertia tensor is still a multiple of the identity matrix. Questions? Okay, so now we're going to move into away from the line and into this region, so I guess the mildly repulsive region was everything up here, but we're going to move into this region over here. And so somehow what broke this problem open for us was the following, being able to penetrate into this region and not needing to assume A was large, was the following simple but powerful monotonicity observation, which is that the observation is that if the simplex minimizes at some point here, then it also minimizes at every point above that and every point to the right of that in parameter space. So on this whole rectangle. And moreover, even if it's not the unique minimizer here, it is the unique minimizer at every point above or to the right of that. So we call that the northeast comparison principle. So if unit simplices minimize at some point, they uniquely minimize at any point to the right or above in parameter space. And moreover, I shouldn't have used A and B. I should have used 1 and 2 since I'm using A and B for my variables. Moreover, remember I said that whenever the simplex minimizes or whenever anything minimizes, the support of that thing has to concentrate on a set of minimizers of this potential. When I move above or to the right, that not only does it have to concentrate, this becomes an equality. So it's not just in general, it would be a containment, but it has to become a equality. And more or less the proof of this is that if I study the potential as a function of the radius, and so it was minimized at 1. And if I normalize this depth of this potential to be -1 by dividing by its value at 1, then I get this very symmetric expression in A and B. And when you differentiate that with respect to either of the variables, it turns out what you get is non-negative. And equality holds here if and only if I'm at the point where I've normalized or I'm at the origin. And these are exactly the distances. Distances 1 and 0 are exactly the distances between different particles on the vertices of a unit simplex. So this particle is distance 1 from this particle, it's distance 0 from the particles on itself. And so when I make these parameter perturbations to increase A or increase B, if I'm a unit simplex, my energy doesn't change after I do this normalization. Whereas if I'm anything other than a unit simplex, then I'll have some particles that are some distance other than 1, and the energy will go strictly up. And so that tells us that already, since we knew this, you can check this, the unit simplex on the unit sphere has moments of inertia tensor proportional to the identity matrix. And that says everything above and to the right of that also has that. And it's also somehow a key ingredient in showing that there's somehow there's a monotone curve here where everything above and to the right of that curve is going to be uniquely minimized by the simplex. So how do we characterize that curve? Well, now this goes back to my earlier work with Lim, in which we showed that not only was the simplex a global minimum for large A, it was a local minimum for all A, larger than B. And even more than that, there's uncountably many local minima, because as long as B is bigger than 2, because I don't actually have to put equal masses at all the corners of the simplices. I can put unequal masses, and then there'll be some small neighborhood of this measure here on which this and its rotates and translates are the only minimizers. But neighborhood in what topology? That I still have to tell you. And it's very closely connected to this. I want a topology that says if I evaporate mass from the moon and put it down on the Earth, that's somehow a discontinuous operation. So there's a topology that comes from an optimal transportation metric, but it's the limiting topology as the transportation cost goes to infinity, or goes to the infinite power of the distance being transported. And let me tell you what that is in a second. Yeah, and I can come back. So here's the definition. So pick any exponent bigger than or equal to 1. If you have two measures, mu and nu, one way of measuring the distance between them is to ask how cheaply can if I need to move the particles of mu to give me nu. So if I look at all joint measures with these marginals here, and then compute the expected piece power of the distance that this joint measure assigns between x and its partner, if I take the pth root of that, then I get a thing that satisfies the triangle inequality. It's obviously symmetric under interchange of mu and nu. And so it turns out to be a distance that, for a compact set, it metrizes the weak topology on probability measures. And I'm primarily, that's somehow the Kantorovich-Rubinstein-Wasserstein LP transport metric, but I'm primarily in this talk interested in the limit as p goes to infinity of this, which basically says that you try to pair the particles of the first distribution with the second distribution so that the maximum distance traveled is but maximum distance between a particle and its partner is as small as possible. That's the d infinity metric. And that's the sense in which all of this uncountable family of unbalanced, possibly unbalanced measures on the vertices of the unit simplex are local energy minimizers for my problem. But in fact, today I primarily care about the case where the mi's are all equal to 1 over n plus 1, so the balanced case. And so the observation is that this balanced unit simplex is a minimum throughout the entire region above b for a bigger than b equal to 2, bigger than 2. And so if it stops being a global minimum, it can't stop being a global minimum because somehow it suddenly becomes unstable, because there's still a neighborhood of it in this strong topology where, so by the way, maybe I should have said that too. dp metrizes the weak topology, but d infinity metrizes a much finer topology. So there's still a neighborhood of this in this strong topology where my simplicial measures and its rotates and translates are the only minima. And so if it fails to be a minimum for nearby parameters, because either there's a minimum far away from it, or at least it's become marginally unstable to putting mass somewhere far away and creating a very different configuration, which also minimizes. And so that was the alternative we saw in the characterization of, so I can go back to it. It was the alternative we saw here, that either there's a minimum far away if I'm on the critical line, or my potential is reached down and it now becomes equally advantageous for me to put mass somewhere far away. And it was actually this idea that led us to these bounds, the lower bound anyways, because we were studying, say, the equilateral triangle, and we said, well, there are maybe ghost locations here which would turn it into a hexagon. And if I look at VAB star convolved with the equilateral triangle, how do the heights of these ghost locations compare with the heights at these points here? And we found if we go too low in this picture, they reach the same level. And so that's how we got our lower bound. Which somehow a miracle, at least for me, maybe Cameron has better insight into it, why the infinite dimensional limit of this turns into an upper bound. That's remarkable. Okay, and so now I'm running out of time, but I'm also coming to the end of my talk. I can mention there was this work of the PhD thesis of Robert Simoni 8 years ago, showed that these d infinity local minima enjoy certain nonlinear stability properties, but the spherical minimizer, it turns out if you if you put down a ring of particles to make kind of a discrete ring, and then you adjust the radius, this will be a stationary configuration. And if you make the particles finer and finer, it will get closer and closer to this. And that means that this can't be attracting, because in any neighborhood of it, you can find some discrete ring where the smallness of the neighborhood tells you how many points you have to put in the ring, which is stationary. And when you start at that, maybe it's not stable, but it never converges to the continuous ring. And so these global minimizers a priori, particularly the spherical shell, can't be asymptotic. It can't be an attractor, because in any neighborhood of it, there are points that don't move towards it. So in what sense can it be stable? These optimal transport topologies turn out to answer that. So there's another notion of stability, which doesn't ask that everything be attracted to your spherical shell, but it asks that if you start in a neighborhood of the spherical shell, if you want to stay in this neighborhood of the spherical shell of radius epsilon, then for some delta sufficiently small, if you start in this smaller ball of radius delta, then you'll never leave the neighborhood epsilon. And it turns out the spherical shell has stability in that sense. So here's a classical lemma of Lyapunov that says, whenever you have a coercive function, meaning its sublevel sets are compact at every height, then for every epsilon, you can find a delta such that, and a height such that the sublevel set contains a delta neighborhood of the minima and is contained in an epsilon neighborhood. And that means if I start inside this delta neighborhood, my energy never goes up. I'm going to stay inside this epsilon neighborhood forever. And it turns out that this theorem exactly applies to our situation. So for any B and A with A larger than B, so it's attractive repulsive, and A has to be bigger than 1, then the hypotheses of Lyapunov's lemma that I just showed you are exactly satisfied by my energy, provided I look at the set of probability measures centered at the origin with compact support, and I put the dA. So the transport exponent, the exponent in the transport distance should be the attractive exponent. And then it's really a simple proof combined with a couple of known facts that tells you that the sublevel sets of this energy are weakly compact, so they're dA compact, and that if you start close enough to the minimum, that you never go far away from the minimum. So, all right, so I think that's so that answers somebody was asking about whether these minima were attractors or not, and that's the best answer that I can give to this question. Thank you very much for your attention.